back to math. The first time I came here was in 1994 for a math conference. This is a conference organized by Jerry Cook. Some people were there. It had like 120 people. And what's interesting about that conference was that was sort of when people were very interested in quantum group representations in connection with modular representations of algebraic groups and affine algebras, and then making the connections through that. So I'll actually mention that in my talk. Okay, so this talk is going to be somewhat of a survey, but also present some results. And one of the really main themes is looking at the interplay between the world of quantum groups, where there are sort of non-semi-simple representations. And then the world of complex algebraic geometry. So there's interplay, and we'll see this interplay back and forth, and this is with complex algebraic geometry. And we'll see that we need to actually use some of the ideas from here in order to sort of say things up in the quantum world. All right, so this talk is going to be based on two papers. They came out about a couple years ago. So the first paper is a paper I wrote with Christopher Briesky and Brian Parshall, where we actually compute what are called the support varieties for irreducible representations. And the second paper, which came out a couple years ago, this talks about the cohomology of quantum groups. It talks about the cohomology for both L bigger than the Coxeter number and also L small. And it connects things with the geometry of the nilpotent cone. Right? So it appeared in the memoirs of the AMS. All right, so I'm going to start out with just the basic classical notation for complex semi-simple algebras. So we're going to start with G being a simple, simply connected algebraic group over complex numbers, so you can take like SLN. Frac G will be just the Lie algebra of G. T will be a maximal split torus for G. Now, whenever you have the pair G and T, you always have a root system. And since G is simple, we have an irreducible root system. 5 plus and minus, those are just to denote the positive and negative roots. And then the Borel that we're going to take containing T will correspond to the negative roots. So this is the convention which is used in like Janssen's algebraic groups book. Delta will be just an ordering of the simple roots. Okay. And W will be the Weil group of phi. And then what we'll need is we'll need the affine Weil group too. So the affine Weil group I'm going to think about as being the Weil group semi-direct product with this L times the root lattice. So rho is going to be the normal half sum of positive roots. You can also realize rho is the sum of fundamental weights too. And then alpha 0 will be the highest short root. Okay, and you can actually define the Coxeter number via the highest short root as taking the inner product with rho and alpha 0 check and adding 1. So another way to think about this is you can take the sort of maximal root and then just take the sum of the coefficients. All right. Okay, so what I'm going to do next is I will define the notation and conventions that I'll use in this talk. A lot of this will actually follow what Henning did in his talk, so I really thank Henning for doing a great job introducing the concepts. In my talk, the phi here will be a primitive Lth root of unity. So in his talk, the zeta here, was actually equal to Q. Okay? And I'm going to make the following assumptions on zeta. So I'm going to assume that the root of unity is odd. Okay, so no even roots of unity. And L is bigger than 1. And in the case where the root system is G2, I have to assume that 3 does not divide L. This is a technical assumption. And then I'm going to have the concept of L being good. So this is the analog of being a good prime, for example. Right? So we say that this L, which may not be a prime, is good if it's not divisible by any bad prime for the root system. Okay? So like in type A, there are no bad primes, so L is always good, okay, with these assumptions. And you know, in type like B2 or B4, or sorry, type BN or CN, then you don't want L to be like divisible by 2, which is not. Okay, and if it's not good, we say that this L is bad. All right, so I have a slightly different notation than the previous talk. So this sort of different U zeta Q, this is the quantized enveloping algebra, which is specialized at zeta. So this was the first quantum group that was defined by Henning, the ones without the divided powers. Okay, and then you specialize this at the root of unity. Okay. Now, when you have the root of unity being 1, you can get the ordinary universal enveloping algebra out of that. Okay. So this is just the ordinary universal enveloping algebra over the complex numbers. So this other U zeta is just this Lustig A form that was introduced in the last talk. This involves the divided powers, and then you specialize things at zeta. So this is the analog of the distribution algebra for like an algebraic group. So you're the hyperalgebra. Now, the other player that we're going to have in this talk is what's called the small quantum group. So whenever you have a root of unity, you have a finite dimensional Hopf algebra, which is actually going to sit inside of the Lustig A form specialized at zeta. So this is like taking the divided powers up to L minus 1, for example. Okay? So we have this small finite dimensional, it's not necessarily co-commutative, Hopf algebra sitting inside of here. And it turns out to be the quotient of this quantized enveloping algebra. So this is the quotient of the quantized enveloping algebra, and it sits inside of this Lustig A form. Okay, and this will be an important player in the game. All right, so this is similar notation as before. My plus is on the bottom, not on the top. Okay, so in the last talk, the plus is actually on the top. So we need the integral weight lattice. Okay, so what we do is we just take integer combinations of the fundamental weights, and the dominant weights are just the ones where the coefficients are bigger than or equal to 0. Okay. So as in the last talk, we have simple modules corresponding to the highest weight lambda, which is dominant. We have these induced modules, which were also defined in the last talk. Okay. And then we have the Weil module, and then we have the tilting modules. Right? So my diagram is a little bit different than Henning's, but I think it says basically the same thing. So we have an injection from this induced module into the tilting module. Right? So remember, he was looking at the composition of these two maps over here. There's a surjection from the tilting module. Sorry, is that right? I have this backwards. Let's see. Is that backwards? No, that's right. That's right. Okay. Surjection onto here. And then we have the injection of this L into the induced module and a surjection from the Weil module on here. Okay, so this is the picture that you want. Okay, good. All right, so now let me connect the quantum group theory to the world of complex algebraic geometry. So here's how we do this. So the way we do this is we use cohomology to get this done. So recall that the small quantum group sits inside of this hyperalgebra or distribution type algebra here. And when I take the quotient of this, something really nice happens. I just get the universal enveloping algebra back again. Okay, so so basically, whenever you're talking about characteristic zero quantum groups, you can only apply the Frobenius map once. It's not like when you take an algebraic group in characteristic P, where you can iterate the Frobenius map over and over and over again. Once you apply the Frobenius map once, you're in the world of just ordinary, like semi-simple Lie algebra theory. Okay? Okay, so now let's say I take a finite dimensional module in this category over here. And what you can do is you can look at the cohomology over the small quantum group. All right? So this module is a module for the big thing, the U zeta G. So this cohomology is a module also for U zeta G2. Right? But the small quantum group is going to act trivially on here. Right? So that means it's going to be a module for the quotient. Okay? So it's a module for the universal enveloping algebra. Each piece is finite dimensional, so it's actually a rational module for the algebraic group. All right? So when I start with a module, which is a quantum group module, I apply cohomology, I get out of the world of quantum groups. I get into the world of looking at representations for a complex semi-simple Lie algebra. Okay. All right, so here's a jazzed up way of kind of saying that, and we'll see this in a second. So let's say our root of unity is bigger than h. Then the cohomology yields what's called a naive functor. So what you can do is you can take modules for this small quantum group here. Actually, this should be big U zeta G, to coherent sheaves on the nilpotent cone. Okay, and the reason why is because when I take the trivial module over here, then the cohomology will actually identify with the coordinate algebra. Okay, we'll see that in a second. Okay, and this will actually come up in a more complicated setup later on. All right, so I have to talk about a very, very important result. This result was actually proved by Friedlander and Partial back in the 80s, and then it was proved with lower bounds by Anderson and Janssen. So this is the quantum group version of their result. So you take a complex semi-simple Lie algebra, and let's say that L is bigger than H. So what I'm going to do is I want to look at the cohomology of the trivial module with itself, which is actually a ring under a Yoneda product. So what this theorem says is that the odd degree cohomology will all vanish. Okay? So cohomology in odd degree vanishes. And the even degree cohomology will identify with the coordinate ring on the nilpotent cone. Okay? So there's a way to actually prove this using certain spectral sequences and showing certain spectral sequences collapse, and they identify with this coordinate ring over here. Okay, now more can be said. So this was.
These are Hochschild modules for small quantum.
Yeah, that's right. It's x of kk though.
Yeah,
it's not bimodule. It's just x of the trivial module. So, okay.
So, but these are Hochschild modules for you.
Yeah. Yes, that's right. Yeah. Okay, so it turns out more can be said even when L is small. So that's where we actually calculated for small L's. And we showed again that the odd degree cohomology vanishes. And in most cases, the even degree cohomology can be identified with the ring of regular functions on the closure of a Richardson orbit. Okay, so it's going to be an orbit which is smaller or contained inside the nilpotent cone. And it's orbit of the form G times Uj, where Uj is a unipotent radical for parabolic. Okay. And one of the really important things that we had to use in this calculation was the fact that the higher sheaf cohomology vanishes for the cotangent bundle of these flag varieties, or partial flag varieties. And this theorem is often referred to as the Grauer-Riemann-Schneider vanishing theorem. So we needed to use a theorem which is from complex algebraic geometry over here in order to prove the cohomology result for quantum groups. So I was talking to my colleague Bill Graham about this, and he said that the only proof that he's seen of this Grauer-Riemann-Schneider vanishing theorem which actually uses analysis. Okay, so they use analysis to prove this, and then it's very useful to actually be able to apply this to calculate things in this case. In this case, you don't quite need that strong a result. An open question is, does this actually hold in characteristic P? So we'd love to know whether that's true also in characteristic P. All right, now with the cohomology result, we can actually define what are called support varieties. All right, so here's how the construction goes. So you take a finite dimensional module again, and you take the cohomology ring. Now, the cohomology ring will just act on this just via Yoneda product. So if I take an x or a extension of C by itself, I could just compose it with an extension of C with that. Okay, so I just compose using the another product. And the content of this theorem says that this X becomes a finitely generated module over R. It's finitely generated over this ring. And then once you have that result, if you take a module, then you could take its dual and tensor by M, look at its extensions. This is finitely generated over R again, and then look at its annihilator and look at its maximum spectrum of R over J of M. And that'll give you a subvariety inside the nilpotent cone. Okay. And in the case where M is a module for big U zeta G, this is a G invariant subvariety inside the nilpotent cone. So it breaks up as a closure of orbits inside the nilpotent cone. So there's a lot of geometry which is involved in this, involving the nilpotent orbits. All right, so I just want to sort of, I'm not going to describe all of this, okay? So this is a theorem that's pretty famous. It's due to Arkhipov, Bezer-Kovnikov, and Ginsburg. And they proved this very beautiful result. And what it does is it gives you an equivalence of derived categories. So this equivalence goes between the derived categories of principal block representations for the quantum group over here. Okay, don't worry about the mix. It's just a technical thing that you have to put in to make everything kind of work out. And then coherent sheaves over the cotangent over the Springer resolution. Okay. And then this is perverse sheaves over the loop Grassmannian. Right? And so you can do calculations over here, and then with this equivalence, you can sort of push everything over to this category over here. So this equivalence actually gives you a proof of Lustig's character formula. Now, in this equivalence, I mentioned this idea of this naive functor. So if you take a module here, you can take its cohomology and get a coherent sheaf over the nilpotent cone. So it turns out that that naive functor was actually constructed by Ginsburg and Kumar, and the thought was that it would somehow lift to an equivalence on the derived category level. And that's what Arkhipov, Bezer-Kovnikov, and Ginsburg actually do. They actually lift that naive functor to create this first equivalence over here. So that's what kind of fits into this picture. Now, this theorem is really important for various reasons. So one reason is that it gives a proof of the Lustig character formula. So you can actually compute the character of simple modules for the quantum group via Cauchy-Lustig polynomials. So this was actually proved earlier by work of Cauchy-Lustig going to affine Lie algebras, and then the work of Kashiwara and Tanasaki, who actually proved it in the affine Lie algebra world, and then used this equivalence to sort of push everything over. So this was done in the 1990s. It was actually, I think, announced at the point of this conference in Banff in '94. Now, another consequence of actually being able to have Lustig's character formula is via parity conditions on the extensions, you can compute the extensions between simple modules in the principal block. So we know how to compute all the X with regular highest weight in the principal block. And the dimensions of these cohomology groups are given by Cauchy-Lustig polynomials. And Bezer-Kovnikov used this ABG equivalence and the ideas in this to actually compute the support varieties of the tilting modules. So that was he showed that it was a very powerful machine to actually do calculations with support varieties. So I'm not going to go into the support varieties of tilting modules today. But what I'm going to do next is I'm going to show you how to compute support varieties for the other modules, the ones which are Weyl modules and induced modules, and also the irreducible representations too. Okay, so what I'm going to do next is I'm going to talk about an important idea. This is an idea which can be used in a lot of different contexts. So I kind of want to go over this and sort of promote its use. So in a lot of cases, what you can do is you can grade modules in a very, very canonical and nice way. And with these gratings, they involve making these modules, into Laurent polynomials over here. And there are certain divisibility conditions on these Laurent polynomials which can tell you things about the representations. All right, so this follows work of Partial and Long. So what you do is you define this height function from the weight lattice into half sum of integers. Okay, so you just do it sort of by root combinatorics. So you take d alpha to be this definition over here. Okay, so these numbers are either 1, 2, or 3. And what you do is you express your lambda in terms of a rational combination of roots. All right? And then once you express it in terms of a rational combination of roots, you take this kind of dot product between these r's and these d's, and then you get the weight. Okay? And there's another formula you can actually do. You can just, it's a half sum of these quantities over here. Okay? So these quantities here are integers. So that means that everything's at a half sum. Now, when you take a representation, you can break it up in terms of its weight spaces like this. Right? And now what we're going to do is we're going to use this weight over here to make a graded character. Okay, so what I do is I look at this sort of graded dimension first. Okay, and I take the weight spaces and I put in a t. So it's a t to sort of separate the weight spaces out. And I put an exponent of -2 to the weight of lambda here. Okay. So when I put in -2, of course, this becomes just an integer. So I just get something which is a Laurent polynomial. All right. So and then the standard notation for character, of course, is you just take the sum of the weight spaces with these e lambdas. So what I'll do next is I'll show you what happens in terms of like the Weil character formula in terms of this definition. Okay, so here's how what we do is you'll notice that these inner products are sort of like Weil's dimension formula up here, except I sort of exponentiate. Right? So you set d lambda t to be this object over here, where I'm taking the product over all positive roots. So this is like the numerator in Weil's dimension formula, right? So what's the denominator? Well, when the denominator is when I set lambda equal to 0. Okay. So the theorem says that if your character is sort of given by a Weil character over here, then your graded dimension is just going to be the quotient of the numerator here with lambda, and then when you put lambda equals 0. Okay? So we call this Weil's generic dimension formula. And then when I specialize at t equals 1, I just get the classical dimension formula that way. Now the advantage here to this is that instead of taking divisibility by like certain numbers, the advantage is that we can actually divide by certain polynomials. And that gives us more information than just dividing by numbers. Okay, so that's why we're doing this. Okay. All right, now the nice thing about this is that we can now compute the dimension of support varieties using this divisibility. So, so this is sort of a technical thing. So if you take a root system, you can look at all roots where d alpha times rho alpha check which is equal to the weight, is just a multiple of L here. So you're just looking at all roots which actually satisfy this. And if L is bigger than or equal to H, then this d alpha plus of L is going to be equal to 0. Okay. So we need to use this when we're talking about small L. Okay. All right. So so this theorem actually, the L bigger than H shouldn't even be here. So we don't even need this condition. So just let L be M, a finite dimensional module for U zeta of G. All right. So this is a theorem that we proved in 2002. I think Ostrich also proved a version of this too in his paper. So what it says is that if I have a module like this, then I can get a lower dimension of bound for the support. The bound for the support or dimension of the support variety by just taking the number of positive roots minus this quantity up here, minus 2 times s plus 2. So where does the s come in? Well, the s comes in terms of looking at the L-cyclotomic polynomial when it divides or when it doesn't divide the dimension or graded dimension of it. Okay, so this gives you a connection between the graded dimension of the module, the visibility of certain cyclotomic polynomials inside the graded dimension, and being able to push the dimension of the support variety up.
You mean to say this is the smallest positive integer that doesn't divide?
I think it's any. We're going to use the smallest later on.
But I mean, if you allow any, then you can subtract any 2s from...
Yeah, maybe it's the smallest.
So you would...
Yeah, maybe it's the smallest.
The theorem is stronger if s is small.
Yeah, I think that's probably right. So, yeah, we're going to use it when s is the smallest. Good, thanks. Okay, so now what I'll do is I'll give you an idea of how to actually compute support varieties for these induced modules. So induced modules and vial modules, they're going to have the same support varieties, so we can just do it for the induced modules. So here's what the theorem says. So what you do is you take all the roots where if I take this particular lambda, then lambda plus rho alpha check is a multiple of L. Okay, so the way you should think about this is you should take your lambda and you're looking at the affine vial group. Right? It's going to sort of divide up the weights. And you're just looking at where lambda sits. And if it sits on a bunch of walls, you're just kind of counting the walls using this invariant order up here, this phi lambda. And it turns out that the phi lambda, as long as L is good, is going to be a subroot system of phi. So that means that I can conjugate this phi lambda via some vial group element in terms of a base consisting just of simple roots. Okay? So given a lambda here, I can always conjugate via the vial group into this base consisting of simple roots. Okay, so once I do that, let me just write it over here. So once I have this J, then I can just break up the Lie algebra in terms of its Levy decomposition. Like this. So that's how I get the Uj plus Uj. And then what the theorem says is that if you pick a lambda, you do this procedure, then you just saturate by the action of the group. These will consist of nilpotent elements, and that gives you the answer for the support variety. Okay, so it's actually the closure of an orbit. It's a closure of what's called a Richardson orbit inside of that. So, just remark that. Keep in mind that G times Uj is always sitting inside of nilpotent elements. Okay, so this theorem was initially, well actually the theorem was a conjecture of Janssen for algebraic groups, and it was stated for P good. Oestrich proved it for the quantum case when L is bigger than H. So we actually proved it for the P good case, and with Bendel, Partial, and Pillen, we extended Oestrich's result for when L is good. So we can actually do things when L is less than H2. So, yeah. And even when L is bad, we have calculations too. And it turns out when L is bad, these orbits here need not be Richardson orbits. Okay, we can actually pin down which orbits they are inside the nilpotent cone, and they need not be Richardson. Okay, so how do you prove a theorem like this? All right, so there are two things you have to do. So first of all, you have to prove this inclusion up here. All right, and the way you actually prove this inclusion, I'm not going to go over the details, but you need certain spectral sequence techniques. You need to think of the cohomology of the supports as being sort of localization at certain maximum ideals of the cohomology ring. So that helps to actually prove this inclusion. And then you also need sort of the theory of relative support and the representation theory, including baby Verma modules. So there's a lot that kind of goes into this, but I want to kind of press that under the rug. All right, what I want to concentrate on was the application of the graded dimension. All right. So since this G times Uj is an irreducible variety, in order to show equality, I just have to show the dimension of this one is equal to the dimension of that up here. Okay, so I have to show this equality up here. We know what the dimension is. It's just the number of roots minus the number of roots, the root system generated by J. And what we can do is we can show that this is true using the MPV result by plugging in this quantity equal to phi j. Okay, so we want an S which satisfies this down here, and the S which will do it is phi j plus minus this quantity plus 1. Okay, so what we want to do is we want to show that phi Lj, so this cyclotomic polynomial to this to the S will not divide this graded dimension. Okay, so let's look back at the formulas. Okay, so this was the formula for this graded dimension over here. Okay. All right. So now you just observe a few things. So first of all, observe that this thing up here. So if I take phi j plus, that's the same thing as phi lambda plus. Okay. So this phi lambda plus connects to this inner product here and here. Okay. This d phi plus L connects to looking at the weight, whether it's a multiple of L over here. So this is just the multiplicity of this cyclotomic polynomial as a divisor inside of this. Okay, so that's not hard to prove. So that means that if I add 1 to this number over here, it cannot divide. Okay, so the multiplicity is actually this number here minus 1. So this number here minus 1. So that actually proves this. So this is actually not too bad because you sort of know that this is related to looking at cyclotomic polynomials. If you just divide by this exponent on the bottom, then you'll get like something to the power of minus 1. You can just do the calculation. Okay, so that's not so bad. All right, so now the next challenge is to do this for irreducible representations. Now, for people who know about the listed character formula, your irreducible representation character is given in terms of characters of these induced modules. And then the coefficients involve Cauchy-Listig polynomials. Yeah? Okay, so we'll get to that in a second. All right, so this is just sort of formalism that I'm going to put up. I'm not going to read over everything. So the idea is that you start off with the affine Weyl group, okay? And it's generated by some subsystem. If you take a subset inside that subsystem, you can define sort of, you can take sort of Levy Weyl groups, right? And then I'm going to let this less than or equal to denote the Chevrolet-Bruhal partial ordering on the affine Weyl group. Now for affine Weyl groups, you have Cauchy-Listig polynomials associated with the pair, y and w. Now, Deodar introduced 2 generalizations of Cauchy-Listig polynomials called parabolic Cauchy-Listig polynomials. So the parabolic Cauchy-Listig polynomials depend on your choice of this subset I, and then a root of this polynomial down here. Okay, so root is either going to be minus 1 or q. And so, so what you can do is you can relate these polynomials that Deodar constructed, these parabolic Cauchy-Listig polynomials, with these ordinary Cauchy-Listig polynomials in this way. All right. Now, there's a little fine print in here. So notice this 1 up here. So this is the one corresponding to u equals q. Right? But notice there's a minus 1 up on top. So it turns out that we're using the Kashiwara-Tanizaki convention. So the q and the minus 1 are switched. Okay, so but that's not going to matter so much, but there's a little fine print on it. Okay, so this is the one corresponding to the q instead of the minus 1, even though I put a minus 1 at the top. Now, there's several basic properties about Cauchy-Donalistic polynomials. So one of them is that we get 0 in certain cases when y does not dominate w in terms of the Bruchal order. And then the more important property about Cauchy-Donalistic polynomials is that the coefficients here are non-negative integers. Okay. All right, so we're going to use this in a second. All right. So it turns out that if you take a weight, or just take a minimal dominant weight for lambda, so what I'm going to do is I sort of index things in the following way. So I'm going to start down at the anti-dominant chamber. So this is like the type A2 picture. So you know your chambers look something like this. So this is sort of the dominant region over here. So I'm going to start down in the anti-dominant region. So this is going to be CZ minus bar. Okay. So I'm going to start reflecting things up into the dominant chamber. Okay, so that's what C minus Z bar looks like down here. Okay, so then once I do that, so I take this weight and I just reflect it into the dominant chamber, I get this lambda over here. Right? And then what you do is you reduce W in terms of the reduced expression. And then what you can do is you can express the character of the irreducible representation in terms of the characters of the Weyl modules over here, and then via these parabolic Cauchy-Donalistic polynomials. Okay, so this gives you a formula. Now, if I apply just a graded dimension, then this character becomes sort of the graded character over here, and so you get this formula like this. Okay, so this is the theorem that we proved. So we proved that the answer is the same. So when you have L being bigger than H, then the support of the irreducible representations sort of just depend on the stabilizer up here. And it's the closure of this Richardson orbit. Now, the nice thing about this theorem is for support varieties, support varieties have been around for like 30 years, maybe almost 40 years. There are not many calculations of support varieties. So this theorem actually gives the most extensive calculations support varieties for irreducible representations for like a wide class of algebras. Okay. But as you'll see, the calculations are rather, you have to use tricks. You have to use like every dirty trick in the book in order to actually calculate this. Okay. So let me show you how to do this. All right, so one direction is not so bad. Because your irreducibles are sort of linked to this, these induced modules, you can sort of induct up on them and then use the prior result via the weight ordering to show this inclusion. It's a pretty easy exercise. Now, in the prior calculation, what did we need to show? Well, we need to show that phi, the cyclotomic polynomial to the s, doesn't divide this graded dimension. Where here, we don't have to worry about the d, okay, because L is bigger than H. So where this 2s minus 2 is equal to phi j, okay? So that is that this is not a root of multiplicity phi j plus 1, okay? So I need to show that this is not a root of this multiplicity over here. Now, it's not so easy, right? Because, I mean, I don't have a nice, like, formula where I'm expressing this dimension in terms of a quotient, right? And this is given in terms of Cauchy-Donalistic polynomials. Okay, so I'll ask you a question. So whenever you want to show that a certain thing has or certain value or root has a certain multiplicity, what should you do?
Differentiate?
Yes, so I mean, So the idea is like this is what you tell your Galois theory class, right? So you start differentiating, and then you find out when you don't get 0. Well, that's what we have to do. Okay, so remember that this is the formula for this graded dimension over here. Now, because L is bigger than H, I can get rid of this D0T. All right? Okay? So what I can do is I can just sort of look at this function f of t where I just kind of divided everything out. All right? This part's not going to matter at all. And so, so you want to know the first spot at which the derivative is not equal to 0. Okay? So once you know that phi occurs as a root of f with multiplicity exactly equal to n. Okay? So what we do is we set n to be equal to the positive roots in the stabilizer, which is the same as the positive roots in this phi plus of j. Okay? And it's the same as phi plus of any linked weight, too. Okay? All right, so now we know that this thing occurs from the previous result precisely n times, because we have the Weil's sort of graded dimension formula for that. So, but it remains to show that this derivative, this nth derivative, is not equal to 0. So once we show this nth derivative is not equal to 0, we can apply this MPV result, and we're good to go. All right, so this thing is a sum up here. This whole thing is a quotient with a product. So we have to take like the product rule and over and over and over again, and then keep track of everything. So here's what happens. Something very magical. So you differentiate this function n times, and here's what you get. So certainly the derivative is linear, so you can do this. Okay, that's no problem. All right, and then you start taking derivatives, and what I'm going to do is I'm going to just keep track of things. I'm not going to tell you what these quantities are over here. I'm just going to tell you that they're not equal to 0. Okay? So when you take the derivative, you just keep track of everything. You define this E lambda minus just to make sure that things don't get out of hand. Okay, so let's look at the bottom term. So we want to show that this thing is non-zero, right? So now this term here is not going to be equal to 0, right? This term here is also not going to be equal to 0 because lambda is dominant and the d alphas are always like 1, 2, or 3. Okay? So this is a sum of certain coefficients of non-zero terms. Now you have to use the fact that the Cauchy-listed polynomials have positive coefficients. This is where it comes into play. All right? So each of these things is positive. Right? So at least this is going to be bigger than or equal to 0. But we also know that when I take w and w, this thing is actually equal to 1. Right? So this has to be strictly positive. And that doesn't work. Okay, so in order to pull off this calculation, you actually need to use the positivity, some deep result in terms of the positivity of the Cauchy-listed polynomials to do this. I'm not sure if this technique will generalize or it will extend to other situations, but it turned out to be a very, very powerful trick in our context. All right, now let me connect things up with the positive characteristic situation. So Henning touched on this in his talk. So if you take a simply connected algebraic group, you can look at the first Frobenius kernel. You could talk about support varieties over that. And it turns out as long as this listed character formula holds in that case, for all restricted dominant weights, you get the same answer. All right, so we know that the listed character formula holds as long as P is very, very large, due to work of Anderson, Janssen, and Sergel, and also a more sort of concrete bound by Fiebig. Okay? And Williamson has shown that the listed character formula can fail even when P is bigger than H. So he has those counterexamples in type A where the listed character formula fails. So we don't know whether this theorem is true for P bigger than H in general. Okay? Only when the listed character formula is true. Now, what would be really interesting is if this theorem failed, even for P bigger than H. So it would be interesting to know when the list of character formula fails, to know whether the support varieties of irreducibles is actually given by this formula or not. Now, the interesting thing is that the X are going to be different. So the extensions for these modules has to be different when the list of character formula fails. So the question is, does that sort of manifest itself in calculations like these? So, you know, one thing to do is kind of look around the Steinberg wave, which is what Williamson did, sort of calculate support varieties in that region. Okay, so I have a few minutes, and in closing, this is my open problem session. So let me give you some open problems, which might be of interest to people. All right. So we know that the from the proof of the list of character formula, we know how to compute x when lambda is a regular weight. So I believe it's still open when lambda and mu are singular. So when lambda and mu are on walls, what does this x look like? Also, what does the x look like when L is smaller than h? That's an open question too. So it'd be really nice to be able to compute this or give some way of computing this using some combinatorial techniques, maybe p-canonical basis, who knows. Okay, another problem that arises in the area is for Lie algebras, it turns out we have an explicit description of these varieties in terms of certain subvarieties of the no-Potent cone. So if you take a quantum group module, how do you actually describe the support variety? So in the Lie algebra situation, you can just restrict down to one-dimensional subalgebras, and you can actually ask whether it's projective over these one-dimensional subalgebras, and that gives us the description. But in quantum groups, it doesn't make sense to just restrict down. Okay, it's much more complicated. So we'd like a really nice, concrete description of these, not cohomological, just in terms of the intrinsic properties of the module itself. Now, on that note, there's this connection at affine Lie algebras. So this is the Cauchy-listic equivalence. So for certain values of k, so this is the untwisted affine Lie algebra, and we're looking at sort of category O for this, right? And so for certain k's, we have an equivalence of categories, equivalence of tensor categories between this category here and modules for this quantum group. And what would be really nice is if there was some way to connect the two in terms of the support varieties and cohomology. So through this equivalence, can we actually pass information back and forth? Okay. And another intriguing question that I think Michael and I looked at fairly recently was, if you have Frobenius twists over here in this category. You can twist modules. What does that correspond to over here in this O of k? We actually have no idea what happens in that situation. Really interesting to figure out what happens to the Frobenius under this equivalence. Okay, so with that, I'd like to thank you for that.
Are there some questions? So you took Q or zeta as odd.
Yes.
So is it something special for you?
I think it's much more complicated.
Right.
It hasn't been worked out.